Well, good morning, good afternoon to everybody. Thank you to be here. The Instituto Politécnico Nacional welcomes you to the webinars Terahertz applications based on emergent and high-performance electronic devices. These talks are part of the activities dealing with Eugenio Méndez Docurro Institutional Chair 2021. These webinars will be held in English. The questions, this is an announcement to the public, the questions can be sent by using the question and answer chat in the Zoom platform or by using the YouTube chat. Today, there is a change regarding the first talk. And the first speaker will be Dr. Martin Hartmann from Technische Universitaet Chemnitz with the talk Geometry-Dependent Performance of Carbon Nanotube-based Analog High-Frequency Field Effect Transistors. Dr. Hartmann received the Bachelor and Master in Science degrees in Physics from Chemnitz University of Technology in Chemnitz, Germany, in 2012 and 2014, respectively. He is currently working with the Carbon Nano Device Group at the Center for Microtechnologies Chemnitz and Center for Advancing Electronics in Dresden, in the field of carbon nanotube device technology with special focus on RF CNT FETs. Please, Dr. Hartmann, can you share your screen?
Yes, sure. So thank you for the kind introduction. Just give me a second, please.
Yes, just a last direction. Dr. Hartmann, you have 30 minutes for the presentation, and there will be a 15-minute questions and answer session. Thank you. On your own.
Okay. So thanks again. My name is Martin Hartmann. I'm not yet a doctor yet, but I'm looking forward to this, I hope, in some weeks. So today I would like to give you some impressions about our work on the carbon nanotube-based field effect transistors and also what has been done by other persons. I'm working in the carbon nanodevice group here at the Technische University Chemnitz. And first of all, I would like to thank the organizers, especially Anibal, for inviting me here to this nice webinar about terahertz applications. And we will see how the CNT FETs fit here within the field of terahertz devices. So our group and also a lot of other groups, they are highly interested in the carbon nanotube as a semiconducting material. And why is this the case? So this is just an excellent material. Okay, this is a material with an intrinsic mobility. This is so high, almost no other material has a mobility that high. And this is even higher than silicon. And also if silicon is highly doped. And moreover...
Sorry, Martin, we
yes?
cannot see your slides.
Okay, none of them?
No. You can use the bottom share screen at the bottom of the screen.
I did that. I can do it again.
Please. Now it's okay. Can you activate full screen, please? Perfect.
Oh, now better? Okay.
Yeah.
Good.
Go ahead.
So, okay. So we were talking about the properties of the carbon nanotubes. Okay. So CNTs have a really high intrinsic mobility. And moreover, they can endure a quite high current density. And these two facts together make them highly excellent material for high frequency field effect transistors. Okay, but these properties, they are known in the past. A lot of scientists have studied the CNTs, their properties, and so on. And they also have built some devices from them. However, to bring them to really or to facilitate their nice properties fully and to bring them to devices and to systems, this is still a route that has to be walked. And we are within the carbon nanodevice groups, we are working on this topic to bring the CNTs into real applications and into real systems. Okay. And besides these two properties, there is some more that are really promising, like their inherent linearity. So theory predicts that there's a high linearity between the input signal and the output signal within an CNT FET. And this makes the transistor highly energy efficient because you don't need to filter, and you also get a broader bandwidth. Moreover, this is a surface-only material. Of course, this is also true for other one-dimensional and two-dimensional material, but this is a big advantage because you have an ultra-thin body. It's just out of 2 atomic layers. So it's just 2 atomic layers thick. And this results in a high or in an excellent gate control. And moreover, if you would scale down bulk materials, such as silicon or whatever, then at small dimensions, you end up with a lot of surface. And these surfaces create a lot of surface defects or dangling bonds that you need to take care of. And this is nothing you need to deal with 1 or 2 dimensional materials. This is a great advantage. And moreover, CNT FETs show partially ballistic transport even at room temperature. Okay, and this of course is related with the high intrinsic mobility, but also this results in a good noise performance of such a device ideally. And the last point that I would like to make here is that this is a substrate-free technology. That means you can integrate CNTs on almost any rigid substrate, okay? So you're not limited to monocrystalline silicon or sapphire or whatever substrates where you need to grow your semiconductor on top by epitaxial growth or whatever with a really high purity. This is nothing you have to do when you work with CNT FETs, okay? You can deposit them on rigid, you can deposit them also on flexible materials for flexible systems, but still with the performance close to silicon-based devices. And moreover, you can think of 3D integration. You can stack them on top of each other, or you can even stack them on an current or incumbent technology, like on top of silicon CMOS, to combine the advantages of both worlds. So the CNT world and the incumbent, for example, silicon world. And just to give you a little more idea, so why CNT FETs are highly interesting. So in 2019, for example, Rutherglen published a paper where they've already showed that their RF CNT FETs showed a higher speed performance compared to the red line to the compared to silicon CMOS devices. So for the given technology node, which was here a little bit above 100 micrometer, the CNT FET was just faster in terms of the extrinsic transit frequency compared to silicon CMOS devices. However, they were not as fast as gallium arsenide pHEMT devices, but with the gallium arsenide devices, you get some issues when you go to smaller channel lengths, so when you scale them more down. And we think that these issues are not occurring for CNT FETs. That means for shorter gate lengths, the CNT FET should also surpass the gallium arsenide pHEMT devices. However, these devices are not optimized yet. There's still a lot of research going on. For example, what we are doing is that we look on the geometry of those devices. So especially the spacers between the gate electrode and the source electrode, the gate electrode and the drain electrode, and also this gate length. So, and why are we doing this? Because these electrodes, they couple, okay? There is a certain capacitance between these two things, parasitic capacitances, and they usually make your device slow. However, you also need to control the contact area here between the CNTs and the metal in order to reduce the barrier to make the device as fast as possible. Okay, and colleagues from TU Dresden, so from the group of Professor Schröter, in this case it was Sven Motis, they simulated such devices. So there were geometries rather similar to our devices, and they simulated the transit frequencies for certain Schottky barriers at the contact sites between the CNTs and the metal, and for certain spaces. So what they varied was actually, they varied here in this case, the gate length, and then they studied the frequency response for that. And what you could see here at first is that when you reduce the Schottky barrier, of course, the transit frequency is increasing. And when you reduce the spacer here, it's also increasing, but just until a sweet spot. So here, there you have the highest speed. And when you reduce the spacer further, then the speed is decreasing. Okay. And then they went one step further. They also simulated the linearity, okay? The linear region of the CNT FETs. And this is shown here by those contour maps. And you see that somewhere over here, this is the region of highest linearity. And you see that this does not superimpose with the region of highest speed. This is quite interesting. So you could either have a high speed or a highly linear device. This is what they simulate. Okay, and we are technology guys, so we wanted to build those transistors to check the validity of these simulations. And this is also what we did. And now after this quick motivation, I would like to give you a little review, what has been done in literature in the field of high frequency CNT FETs. And then I will give you an overview about our technology, how we build our devices and what are the results. So what is the geometry dependence really of the speed and of the linearity of our CNT FETs. And finally, I would just sum this up quite quickly. Okay, so here I have a little plot where I plotted the transit frequencies or the speed of the devices, which has been published in the different years, so over the time. So it's the first device. So this is not one of the first device, but the first devices were built quite a while ago, and this was all motivated by simulations. Okay, so different simulations they prospected here, and transit frequency above 1 terahertz. And here I need to mention that I'm comparing a little bit here apples with pears, because the different devices here have different channel lengths, also different CNT densities, but it's just to give you an impression how this field of CNT, high frequency CNT FETs evolved over time. For example, when we look here at an early work by Luan and Api and others, then we see that they built high frequency CNT FETs with a rather long channel length. This was longer than 8 micrometer, but they still could realize a device with a transit frequency of about 11 gigahertz. And I'm always speaking here about extrinsic values of the transit frequency. Okay, and then over the years, the design changed a little bit, and then Kao and others, they used a self-aligned T-gate approach to structure and top gate, and then they structured the source and drain electrodes by using this T-gate to self-align them to reduce the parasitic capacitances to its minimum. And thereby, they could increase the transit frequencies to, I think it was around 70 gigahertz. So that was quite nice. And we went a little bit different approach. We usually don't use a top gate, we use a bottom gate, and we use a multi-finger bottom gate approach. And this reduces the gate resistances. However, you get there some challenges with parasitic capacitances, but this is something that we could solve. So we realized this was such multi-gate finger devices, and I will come to this later on again. And we used a random orientation of CNTs to study their geometry dependence. Okay, and then in 2019, Rutherglen published a nice paper where I already showed you the results, where they could show for the first time that for given technology nodes, the CNT FETs were faster than silicon-based CMOS transistors. And they could achieve that because they integrated CNTs with a much higher density, so up to 40 CNTs per micrometer, and they reduced the channel length here a bit more. So we had a channel length here of about 280 micrometer. This was a little bit longer than 100 nanometer. And quite recently, there was another publication from the Peking group here by Shi et al. And they could show transit frequency of such an RF CNT FET of above 130 gigahertz. And they achieved that by further reducing these this channel length. Okay, that was here, I think 95 nanometers. That was not the shortest channel that they fabricated, but I think this is best to compare with the publication from Rutherglen. And they further increased the CNT density in the layers almost to a point where it's really, really difficult to judge on the actual CNT density, but they state something like, I think it's above 80 CNTs per micrometer. However, there is still a gap to the theory, and this is due to the fact that you really need to control 7 important technological aspects of those CNT FETs. So when you think or imagine a CNT FET, so this is quite easy picture here of it, with a bottom gate and gate dielectric and the source and a drain contact, and in between is the semiconductor. Here are the CNTs. Okay, and now when we take a deeper look into it, we see that there are a lot of important aspects that you need to consider. One thing is the contact, okay, the source and the drain contact. So you would like to have here a really small or an almost vanishing barrier. And this is quite difficult to achieve. In literature, you read quite often, okay, use palladium as a contact material and you get ohmic contacts. But this is not fully true. And there's one issue with palladium. Palladium doesn't stick properly on oxides. Okay, so you always need an adhesion layer. And then you need to consider the interaction between the contact material and the adhesion layer. You might get some metal interdiffusion, some alloys are forming. This changes the work function of the material. And then you get a different barrier here at the contact sites. Okay. Another important aspect is that you need to remove all the residual molecules here at the contact site and also on the CNTs in order to get an ideal contact. Okay, so this is one thing. And of course, you can also use other materials instead of palladium. We usually use platinum, but there are also gold or titanium are quite common materials. And this also depends whether you would like to have an N or an P type device. And the next thing is that you need to keep in mind are the ambient molecules. Are there ambient molecules close to the CNTs at the contact sites or in the channel region? For example, water and oxygen is known to act as really, really strong P-type dopant on the CNTs. And when you now, for example, passivate your device, so you remove the water and the oxygen from the device, then your current drops quite a bit and your threshold voltages shift, and you need to invest quite some effort again to get this P-type doping again, to get the performance of CNT FETs passivated when you compare them to unpassivated devices. And this is quite interesting. And this doping is a big topic now for 1- and 2-dimensional materials, because when you want to dope them, you cannot do it by direct chemical doping, because then you usually destroy the nice crystalline structure and you don't have the excellent properties of the nanomaterial anymore. So you need to think of electrostatic doping. And you can do this intentionally or unintentionally due to mobile charges, static charges in your oxides, in your layers that are around the CNTs. You can have interface dipoles if you have their interface between different materials. And all of these charges and dipoles, they electrostatically dope your CNTs. And you really need to control them in order to facilitate the best properties of the tubes. Yes. And then you also need to take into account whether you do some pre-treatments. When you do some annealing, for example, afterwards, this enhances the metal diffusion here, but also carbides can form. Okay, so you somehow decompose a little bit the CNTs, the carbon goes into the metal, and you can either form direct bonds to the metal, or you change again the work function of the metals here. So this is again something you need to keep in mind. Another important aspect is that you need to use CNTs with a low defect density, and your pre-treatments should also not increase the defect concentration on the CNTs too much. Then we want to use a certain chirality of the CNTs. That means a certain crystalline structure of the CNTs where we only have semiconducting and no metallic CNTs. And then another important aspect is the assembly. How are the CNTs assembled or arranged? Because we want to bridge the source and the drain by the shortest possible distance, and we want to reduce the interaction between the CNTs. And this is especially important when you think of analog CNT FETs, because these facts here are in general true for CNT FETs, whether you want to use them for analog RF application, whether you want to use them as sensors or for other stuff. But when you look for analog high frequency CNT FETs, there are some more aspects that you need to keep in mind. Okay, one is the exact geometry and the spacer, because you have a certain capacitive coupling between the electrodes, so the drain, the gate and the source, or source and drain. And these capacitance are parasitic capacitance, and of course you want to reduce them or put them to minimum in order to have the highest operation speed of your device. So you need to have here a quite precise alignment between those metal layers. But nevertheless, you also want to change the spacer in order to have control over your contact region. This can be beneficial, but just to a certain extent. And this is the main part of the research that we did quite recently. Another important aspect is that you need to think of a proper material for the gate. It should have a low resistance to reduce the overall gate resistance. And the question is also how many of these gate fingers to use in parallel to reduce the gate capacitances. the gate resistances. And then the last point that I would like to mention here is the CNT density. Okay, so ideally you have a really high CNT density, so with a spacing of about 5 nanometers, so that the interaction between the CNTs is not so strong, but you have a lot of them integrated, so you can reduce the size of your device, and this further reduces parasitic capacitances. So all in all, there are a lot of aspects that you need to cover. Not all of them are optimized yet. There's a lot of investigations going on to improve them. And I think there's a lot of room for improvement to boost further the frequency performance of such transistors. Okay, now I would like to give you an overview how we build our devices. So we work with 200 millimeter silicon wafers. So we are not, or in literature, the biggest wafer size that I saw there in publications was around 100 millimeter wafers, so 4-inch wafers. But we work together with some companies and some other fabs, semiconductor fabs. And for them, it's really mandatory to work with 200 millimeter wafer to combine our technologies there. And this has a big advantage because then you fabricate a lot of CNT FETs in parallel. You can add a lot of variations during the processing to really optimize the devices. And we do all our processes then, this is mandatory on the wafer level. So these are all wafer level processes. We don't do any pick and place also. This is not what we do. And we usually start with silicon wafer. We grow some thermal oxide on top of them. And then via a Damascene process, we structure the gate electrodes. So Damascene process means that at first we etch into the oxide some trenches, we fill it with metal, and then we polish away with chemical mechanical polishing until the trenches are filled and you have almost no dishing here between the surface of silicon oxide and the gate. Yes. Then we deposit an high K dielectric on top here. This is typically hafnium oxide. And the next thing is the CNT deposition and the structuring of the CNTs. And we have different approaches to deposit the CNTs. One approach is a printing-like technique. There we can print CNTs with a rather random orientation and with different densities. So we can define the density here by our process parameters. And here it's shown that the CNTs are printed here in thin lines over the entire 8-inch wafer. So we can print them wherever we want them, but not necessarily on the entire wafer, just on these locations where we really need it. We need here just a minor amount of dispersion. This is really almost nothing that we need. And we have the CNTs at the locations where we want them. Not for all application, it's important to have a highly aligned layer of CNT FETs. And when we did the experiments that I will show you on the next slides, and there this process was the most reproducible process that we had. So we also went for this random aligned CNT layer here for our high frequency CNT FETs, because we were not interested in having the fastest device, but we were interested in studying the geometry dependence. And therefore, we somehow need a reproducible or a technique that yields reproducible CNT layers. But we also work on a self-assembly technique where we make use of the liquid-liquid interface between a liquid and a CNT dispersion. So here this color comes from the CNTs, which are swimming here within the dispersion. And by such a self-assembly technique, we can achieve highly oriented CNT layers. So all the black part here are horizontally aligned CNTs with a density above 60 CNTs per micrometer. And here you see some defect lines. So it's not fully ideal yet, but I think this is a quite good level right now. So future CNT, high frequency CNT FETs will be built using this technique. Okay, so however, after depositing and structuring the CNTs, then via a lift-off process, we structure the source and drain electrodes. And this is almost it. So this is the device, how we operated it. And since we used two lithography approach, so one lithography for the gate electrode, one lithography step for the source and drain electrode, we are fully free to design the geometry in any way we want. When you would use a self-aligned T-gate approach, then you don't have this freedom. But in our case, we can do this. We can define all the spaces to the extent what we want. And when you take a look then at the devices here, they look like that. So we fabricate them in a ground signal ground configuration to do the high frequency measurements. And after they are done, we make DC measurements on the entire wafer of the transistors, and then the colleagues at TU Dresden, they measure the high frequency performance, so the S parameters, the scattering parameters of our devices. Yes, so let's take a look at some of these results. So within the first study, we varied the gate length, but we kept the channel length, so the distance between the source and the drain electrode, constant, okay? And by varying the gate length, this means that we increase or reduce here the source spacer, okay? As I mentioned, we had a channel length of about 280 nanometers. This is marked here by the red line. And all the gate lengths above the channel length means that there is an overlap between, or an underlap between the gate and the drain and the gate and the source electrode. And smaller values mean, of course, that there is an positive source spacer here. And what did we see? We see that our fastest devices operated closely up to 14 gigahertz transit frequency, and it corresponds to a maximum frequency of oscillations of about 5.5 to 6 gigahertz. So this is not too high, but when we consider our high channel length, this is quite reasonable. Yes, and then what would you also see here? You see that if you have an overlap, so if you have some additional parasitic capacitances, then the frequency drops quite strongly. This is expected, and that the highest transit frequency is not for the lowest spacer. No, it's for something like a 50 nanometer spacer. So this corresponds to 80%, to a gate length of 80% corresponding to the channel length. Okay, there we saw the highest transit frequency and the highest frequency of oscillation. Smaller gate length, for smaller gate length or for bigger gate length, again, the speed was reduced. And you could, with a rather easy formula, sorry for that, you could correlate the transit frequency to the transconductance of the device and to the total capacitance of the device. So just to understand this behavior here a little bit more into detail, we analyzed the capacitance and the transconductance, so the GM values. And the capacitance trend was as expected. So without an overlap, you have an almost constant, maybe slightly increasing capacitance. And for an overlap, the capacitance increases strongly. But the GM trend was not as expected. We expected that when you bring the gate closer to the source and drain electrodes, you get a better control over the barriers, and the GM is increasing and increasing. However, the trend was true for the first points, but then when you come closer to the channel length, then the transconductance decreased, and that was really surprising me. And so it took us quite a while to think about that, and the real origin is still under debate, but we have two possible explanations for that. So the CNT metal contact is quite a complex thing, because when you have a specific metal on the CNTs, the metal can alter the band gap of the CNT. So here from a metal uncovered CNT, a pristine CNT, and then you take a look at the band gap here of a metal covered CNT, you see that it can be changed, okay? So, and the amount, how much this is changed, can be controlled or manipulated by the gate electrode or the gate potential, okay? And the closer you bring the gate electrode under the source or to the source, the bigger is the impact of the gate field onto the entire contact region, okay? And this means that you can thereby manipulate or alter the contact here, or the Schottky barrier that is at the interface between the metal covered and the metal uncovered CNT region. And this alteration is gate source voltage dependent, and this finally can further reduce your transconductance. So this is one possible explanation. But the other explanation are near contact barriers. So Martin Klaus et al., they have shown that there is a finite probabilities for some charges to be within the band gap of the CNTs. And this probability increases if you reduce the barrier between the CNTs and the metal contact. And if you now reduce the barrier, that means you have more of these charges within the band gap. This can again reduce your overall transconductance. So these are two ongoing theories why the transconductance is reduced. Yes. So let me now come to another point, to the linearity of
4 minutes more, please. Thank you.
Yes, sure. So let me come now to the linearity of our CNT FET. So when I talk about linearity, what do I mean? So I mean the linearity between the input and the output signal. So here in a transfer characteristic, this linear region. And the derivative of ID by VGS is called the transconductance. And so we would like to have here a really constant and transconductance, or due to the relation, a rather constant transit frequency. Okay, that would be fine too. Okay, and you can describe the transport through a CNT here within a CNT FET by a Landauer equation, by the transport through one sub-band. This is a rather long equation. I will not go into any detail here, but within an ideal CNT FET, you have single subband transport, you have ballistic transport, ohmic contacts, and a quantum capacitance, or you can operate them in a quantum capacitance limit. This is what some papers or some theory and easy theory tells you. And what does this mean? If you have ballistic transport and ohmic contacts, you don't have any losses within the tube. That means that your transmission factor T, okay, becomes 1. That means that this derivative vanishes. This T becomes 1. And then furthermore, when you're in the quantum capacitance limit, means that you don't have any tube charge and nothing and no related tube capacitance, okay? That means that the scaling factor M becomes 1. And then finally, your GM is only proportional to the electrical charge and the Planck constant. And this gives rise to the prospected higher linearity. But in reality, it's not like that. You usually don't have just multiple, you don't have just single subband transport, you have multiple subband transport. The quantum capacity limits is not that easily achievable, and you usually have some Schottky-like contacts, okay? So the guys from TU Dresden, they took this into account and they thought, okay, maybe we can introduce a certain Schottky barrier here to avoid a charge backscattering into the source and thereby increasing a little bit, or increasing again the linearity. And this was the origin why they started to do the simulations, and these are the results that I've already shown you. And now we took a look at our results, whether we could confirm this. And first of all, we took at this linearity, or at the constant region of the transconductance for different bias voltages. And we found that if you increase the magnitude of the bias voltage, your linearity or linear region increases. And this is due to mutual screening effects. Okay, and now when we take a look at the gate length, or at the gate length dependence of the linearity, we saw, interestingly, the fastest devices, they show the lowest linearity. And the devices that are a little bit slower, so probably with a little bit higher barrier, they show an enhanced linearity. But the highest linearity we found for the devices with the smallest gate length, that means the highest spacer. And then we went one step further. We thought, okay, the main important barrier is the barrier between the source electrode and the CNTs. Okay, so when we now shift asymmetrically our gate electrodes towards the source, we get an enhanced control of the source barrier, but we reduce the parasitic capacitance towards the drain electrode. So we made asymmetric devices and we studied them. Okay, and what we found here was that the highest transit frequency and maximum frequency of oscillation were achieved for around 0 nanometer source spacer. When you have an overlap again, the speed is reduced, but also if you increase the source spacer, then the speed is slightly reduced. The transit frequency stays almost constant, but the maximum frequency of oscillation is affected a little bit more. And this again can be explained by looking at the gate capacitances, which is rather linear increasing when you bring the gate closer to the source. And again, a similar trend of the transconductance as I've shown you before. And now, interestingly, when we look at the linearity, here we see a little bit different effect. We see the highest linearity for the devices with the highest speed. So this is now a little bit different to simulations, but keep in mind the simulations were done on symmetrical devices. So the impact of the drain spacer here still has to be simulated, and we are also right now studying them in more detail. Yes, and with that, I would like to give you a quick summary. So I hope I could show you that CNT FETs have a really high potential to become a potent candidate for analog high frequency applications, and that you really need to design your devices properly, that there is a dependence of the geometry or of the operation speed on the geometry. So there is an optimal gate length to channel length ratio, and if you further asymmetrically shift the gate electrodes towards the source electrodes, you can further improve the speed performance and the linearity of your devices. Okay, and let's skip this slide. And with that, I would like to acknowledge at first all the members of the carbon nano device groups and all our project partners, and especially the group from TU Dresden, so from Professor Michael Schröter, and also their former members like Martin Klaus, Sven Mutes, Annibal, and Paulo Sakalas. And I would also like to thank you for your attention.
Thank you so much, Martin, for this really exciting talk. Now, we are going to begin the question and answer session. Let me see. Yes, there is a question. Andres Serrano, yes. Can you expand quickly on the reproducibility on the fabrication of the CNT-FETs devices? It asked, what challenge did you find and how critical this aspect is? Which are the main buried gate CNT-FETs device challenges?
Yeah, so the challenges for buried gate CNT-FETs. So challenges, so you need to have the proper device equipment at first, of course, because we do a buried gate approach and a planarized gate. That means that the gate is really, or the CNTs are not bended anymore. So if you would deposit the gate electrode on top of your silicon oxide and then just lay the CNTs on top of that, then you would bend your CNTs, which might introduce some issues into the final device. So you really need to embed them properly to have them leveled up with the silicon oxide, for example, in this case. So this is one issue. Then the surface of the gate electrode has to be really rather smooth, because you want to deposit a hafnium or an high K dielectric on top of them, which is deposited typically by an ALD process. And there you really want to have a smooth surface also to avoid any breakdowns of your gate dielectric. So this is one thing. And of course, you need to have the precision. For example, we use electron beam lithography to define here the positions. So this is a rather critical step here.
Okay, thank you so much. Yes, I have a question, Martin, for you.
Okay.
In your opinion, which are the main challenges in a buried gate CNT-FET technology to be overcome in order to obtain the lowest radio frequency and low noise?
The main challenges in general, right? So
yes, in general.
Something like I've discussed here at the beginning. I think this picture somehow summarizes this quite well. So you need to have a high CNT density. Okay, the CNTs have to be closely packed, but you should avoid CNT bundles. This is really, really critical. And then you have to have really clean and ideal contacts. If you can achieve this, then you already have a quite decent device. And then the next bigger challenge is to design a proper device with a high electrostatic doping of the contact region and also of the channel region. So I think the electrostatic doping is another big fact that is really important, and not just for CNTs, but also for other 1- and 2-dimensional materials.
Okay, thank you so much, Martin. If there is any other question, please use the question and answers chat or the YouTube chat. Apparently, these are all questions. So we thank you so much, Martin, for your exciting presentation. It's a pretty interesting subject. And now
Sure.
we have a diploma. We will send you later because there were a switch between you and Hannibal. So we will send your recognition in an email in the following days. And thank you so much to be here.
Sure, it was a pleasure. Thanks.
Thanks, Martin. There is a question here. One moment, please, from Annibal. Yes. Question number 1. Your work reflects a close interaction between modeling group and the technology group where you participate. Can you comment on the importance of this interaction towards obtaining a successful RF scientific technology, please?
Yes, definitely. So this interaction or this collaboration is really fruitful, really great. At first, we technology guys, we get really a lot of insights on important aspects that this simulation group can simulate, and then we know where we should take special care of. And for the simulation guys, of course, they can simulate a lot of things, but the simulations have to be proven, right, in order to be valid. And this is, of course, something that only we can do. So for them, it's really important to work with us together, but it's the same vice versa. So yeah, I think this collaboration is really, really important.
Okay, just a second question from Aníbal. Are there specific reasons why you do not use a top gate architecture for your devices?
Yes, there is a certain reason. So simulations, also in the group from Professor Schröter, they have shown that when you use a top gate architecture, for example, like in this picture, just move this gate electrode here on top, okay? Then you have a much bigger parasitic capacitance between the gate and the source and the gate and the drain. This is easily imaginable here, okay? So, and this is already one big reason why we don't do that, because a parasitic capacitance, a higher parasitic capacitance means a slower device. And this is nothing that we want to have. Of course, you could think to integrate the source and the drain electrodes now into the bottom layer, but this induces some other technological issues. So I think from technology sides, this is then much easier to realize. And yeah, this is more or less the reason why we did that.
Okay, okay. Thank you. Just a last question, Martin. Which is the passivation material you use in this technology? Okay, so in this case, we didn't passivate the device, so we operated at ambient condition. One reason for that is that this strong p-type doping that I talked about, this is rather beneficial, partially, okay, for the speed. However, in the next term or on the devices we are currently working, of course, we need to passivate them because we want to integrate them into systems, we want to package them, so they have to be passivated. And typical passivation layers here are, again, high-K dielectrics, like hafnium oxide, aluminum oxide, or even silicon oxide works sometimes quite well. But if you want to improve the devices, then you might think of a certain stack of such layers and not just having one material there. Okay, perfect. Aníbal, thanks for the answers, Martin. I also thanks for your answers and your presentation. Thank you so much, Martin. It was a pleasure. Well, I have some time to present our next speaker. So, yes. Our next speaker, Dr. Dimitra Georgiadou from the University of Southampton in the United Kingdom, will present the talk entitled 100 GHz Schottky diodes for flexible large area electronics. Dr. Dimitra Georgiadou, University of Southampton, UK, is a future leader fellow leading the organic and amplifiers, flexible nanoelectronics theme in the Center for Electronics Frontiers at the School of Electronics and Computer Science in the University of Southampton. Previously, she was Industrial Fellow at the Department of Materials, Imperial College London, ICL, working with Pragmatic at UK SME, developing flexible radio frequency electronic devices for the Internet of Things. And Marie Sklodowska-Curie, Fellow at the Department of Physics, ICL, where she is still an academic visitor. Dimitra has so far co-authored 54 publications in peer-reviewed journals. Her research interests are the fabrication of and optimization of nanoscale optoelectronics devices by applying novel material concepts and alternative patterning techniques that are compatible with flexible substrates. Well, Dimitra, you will have 30 minutes of presentation, and then there will be a 15-minute question and answer session. Please, Dimitra, on your own. Thank you.
Thank you very much for your introduction, and thank you for inviting me to be part of this webinar series. Before I start, could you please confirm that you can see my screen and hear me properly?
Yes, it's okay. You can see your slides, and we can hear you properly.
Great. So I am based, as you kindly mentioned before, at the University of Southampton. This is in the south part of England. University of Southampton is one of the top 15 UK universities and one of the best universities globally. My department is the School of Electronics and Computer Science, which was recently ranked first in the UK for electrical and electronic engineering by the Guardian University Guide 2022. Inside Electronics and Computer Science, I am part of the Center for Electronics Frontiers group, where I am leading the flexible and organic electronics theme. The vision of my group is to develop lightweight, conformable, and smart electronic devices of the future. We do that by following an interdisciplinary approach, which is merging nanofabrication with materials engineering and device physics. And we try to add functionality in electronics and achieve breakthroughs in several fields, such as AI hardware, indoor photovoltaics, radio frequency energy harvesting, and the Internet of Everything. So this talk is mostly related to the last application fields. And as you all probably know, 5G has already entered our lives, enabling a great deal of what is known as the Internet of Things or the Internet of Everything via smart homes, and enabling fast connectivity between devices and connecting the devices with humans. 6G is expected to further revolutionize our everyday life. For example, by creating a totally different way of knowing transport, creating networks of connected autonomous vehicles, and unlock the capabilities of extended reality technologies like virtual reality and augmented reality. And who knows, maybe those technologies in the future find application in many more fields beyond the immersive entertainment that they are most popular today. So as we move from the fourth generation to the fifth, and within the next decade to the sixth generation of wireless communication technologies, different parts of the spectrum are used. At 6G technologies, which, as you see here, they extend at the hundreds of gigahertz regime, up to terahertz, more data will be able to be transported much faster, almost 1,000 times faster than 5G, and 4,000 to 1,000 times faster than 4G, which is already kind of behind us. But how does this frequency relate to everyday applications? We can see in this graph the correlation of the operating frequency bands with the read range and consequently the end applications. From short range, low frequency key fobs and contactless smart cards or NFC devices that make use of the 13.56 megahertz part of the spectrum, to toll collection gates, which operate to the ultra high frequency regime around 800 to 900 megahertz, we can see that the security requirements in its case define the operation range. On the other hand, most wireless communication protocols like Bluetooth and Wi-Fi protocols, they are intended by default for longer range communication, and they utilize the 2.4 and 5.8 gigahertz bands. It's imperative to lower the cost of manufacturing these radio frequency devices, which are able to operate at higher frequencies at the gigahertz regime and above, in order to accelerate their incorporation in almost every object we use in our life. To do that, even if we can do it in the special case, we can do it with flexible substrates, then this would enable even more applications in wearables or generally in curved surfaces. For example, a Schottky diode structure is used as a rectifier in an RFID tag, like the one shown here, which comprises an antenna and a chip, and the rectifier is part of this chip. The figure of merit that characterizes the operation of this diode is the cutoff frequency, which, as we can see here, is inversely proportional to the product of the resistance and the capacitance. In order to have high cutoff frequencies, we need to minimize this product. If we now check how the standard Schottky diodes are being made, we see that this is based mainly on a vertical configuration where we have two metals and the active layer is sandwiched between those two layers. However, if we move to flexible electronics and use an active material which is processed from solution, then we have certain restrictions in terms of how thin we can make those films, because in very thin films, the homogeneity is not great, and we may have pinholes in the films as we deposit them. For this reason, we propose a different device architecture, similar to the one shown here. This is a coplanar architecture where the metals are sitting next to each other and they are separated by a very short gap, and the semiconductor, the active layer, is deposited in between this channel. This way we can lower both the resistance based on the material that we use and the capacitance, because as you can see, we keep the footprint of the device the same, but this time the actual area is defined by the width here of the diode and the length, which is the thickness of the electrode, while in this case, it's defined always by this active area of in the vertical device. So at the same time, we can address both a decrease in resistance by choosing the material and in capacitance by changing the geometry, and also be compatible with flexible substrates. However, the greatest challenge here is that to fabricate these nanogap coplanar structures, especially when we want to use asymmetric electrodes to be able to fabricate Schottky diodes, the actual methods to do that, the fabrication techniques are not really scalable. And I'll come to that right away. So the standard nanogap fabrication techniques are electron beam lithography, which can be combined with mechanical controllable break junctions and focused ion beam lithography. Advantages are that with e-beam, we can actually get very small sizes and good quality gap. However, most of the times we get symmetric electrodes, or we need to make the fabrication even more challenging and complicated to have asymmetric electrodes by adding several lithography steps. So it's complex, and the equipment, the e-beam lithography tools are very expensive, in the range of millions of pounds, dollars, euros. And also it's time consuming. In order to draw one line, you need perhaps several hours, depending on the tool you're using. Then there are electrochemical approaches, which are scalable, and we can also make asymmetric electrodes. However, sometimes there are toxicity issues with the solvents used, and there may be consistency issues because the nanogaps one can get with these techniques are not always homogeneous, and they have many protrusions that change the performance of the device. Then we have we can use scan and probe lithography techniques such as atomic force microscope lithography or scanning tunneling microscope based break junction techniques. Actually, with these techniques, one can get ultra short gaps, atomic scale gaps in the sub-nanometer range, and very uniform ones. Again, this is a slow process. It's not yet scalable, and that's why it's mainly used for research purposes. So today I will introduce to you a novel technique. It's called adhesion lithography, and it's an innovative fabrication technique to get coplanar, large aspect ratio, metal nanogap separated electrodes. As you see here, we have these coplanar electrodes. They can be the same or different metal, and they are usually separated by a nanogap of about 10 to 15 nanometers. Also, you can see that on this substrate, for example, we have on one fabrication step, we can deposit plenty of devices on the same substrate. How it works? The main attribute of this technique is that it is based on the modification of surface adhesion forces with self-assembled monolayers. A self-assembled monolayer is a molecule like the one shown here, which bears a functional head group, and this group has an affinity for a specific metal. For example, it can be a phosphonic acid, which attaches to the native oxide of aluminum oxide or titanium oxide, or it can be a thiol group, which has an affinity for gold, for example. The rest of the molecule is a long hydrophobic tail, which does not bind to any metal. However, this hydrophobicity induced on top of this metal changes the adhesion properties of a second metal when we deposit it on top of this some functionalized first metal. And I will explain right now how we take advantage of this property to fabricate our nanogaps. The steps of adhesion lithography process are quite simple. We start by depositing and patterning the first metal with the standard photolithography according to the shape that we choose. And then we dip the patterned substrates in the solution of this molecule I showed before. We leave it for some time, and what happens is that the functional head, as I explained before, will align and attach to the metal, but not on the substrate. So then we just deposit the second metal everywhere without using any shadow mask or anything more complicated than that, and apply a glue that helps us to peel off the second metal. The interesting part is what happens here during this peeling step. The part of the second metal which is in contact with the some functionalized part of the first metal is being removed because the adhesion forces of that metal are weak. On the other hand, the part of the second metal which is in contact with the substrate where no sum was present, it remains on the substrate because the adhesion forces between the second metal and the substrate are stronger. In this manner, we manage to have both metals sitting next to each other, and these are separated only by the sum molecules, which we can easily get rid of by shining a UV ozone lamp on top of it or plasma ashing the substrates. So we end up with an empty nanogap electrode, and then we can deposit from solution the precursor of our semiconductor, and after some annealing, we have the film on top of the pre-patterned electrodes. From what I showed so far, you can tell by yourselves that this is a substrate and pattern agnostic technique. There is a huge versatility in design patterns we can use because they are defined by photolithography. And that's why we can do a lot of scaling studies with these electrodes. For example, here you see on the same substrate how we have scaled those interdigitated electrodes from 1 centimeter to 1 meter. Here we have squeezed 1 meter long electrodes as defined by the perimeter of those fingers in the same footprint as is this case where it's just 1 centimeter long. Also here, just to showcase the potential of this technique, we transferred the pattern of the London skyline. This is the London Eye, and this is the Tower Bridge, aluminium and gold. If we look closer at the interface between those two, here in the Tower of London part, we see with the SEM that the metals are separated and by a homogeneous gap. We still cannot see how big or small is this gap, and we need to go to high resolution TEM, transmission electron microscope, to actually define the scale of this gap. And as you can see here, it's in the range of 10 nanometers. We have also applied this technique on flexible substrates, PET, PEN, polyimides, and Also, we have upscaled to a wafer scale. So from the lab scale substrates, we can also fabricate wafer scales and then cut them to the desired size to do our measurements. The gap is quite homogeneous. We started with the electron microscopy, the homogeneity of this, and we see that there are no distinct protrusions or pointed edges along the electrode walls, as happens, for example, with other techniques I mentioned, like the electrochemical method. The uniformity actually is very similar to the electron beam lithography derived gaps, but of course you can tell by the description I made earlier that it's much cheaper and faster. And also we can have easily, with the same way, without changing or adding any step, we can have either symmetric or asymmetric metals. So now I will show how we used those patterned substrates to fabricate our high frequency diodes. The material of choice here was the zinc oxide, and we fabricated films from a carbon-free precursor solution, which gave us continuous polycrystalline films measured with in transistor configuration, having an electron mobility of about 10 square centimeter per volt second. Then by choosing the electrode configuration of our patterned nanogap electrodes being aluminum and gold, we could have, we obtained a Schottky contact with gold and an ohmic contact with aluminum. So because the barrier height between gold and the conduction band of zinc oxide is quite high. And again, this is a coplanar structure, so we managed to have films which are very thin, but they have no pinholes, so no electrical shorts are happening. You can see here a representative IV of this diode, which shows a quite high rectification ratio, a low reverse current, and it shows first that the electrodes are not shorted if we apply voltage between aluminum and gold. Second, we can see that there is a material, because if no material was in the gap, we would get very low current constantly as we would increase the voltage, while in this case we are quite certain that this performance is due to the material we have used. Then we did a scaling study, which, as I said, is quite simple to do with this addition lithography technique. And we changed the diode width. The diode width in this case, for example, in this geometry, can be easily tuned by changing this part of the electrodes, while in any case, we have a channel length of about 10 to 20 nanometers, and the thickness of the electrodes remain the same. So this is the only part that we change. And we see that the current is, as expected, scaling with the diode width. If we scale it from 200 microns to 5 millimeters, we see there is a linear trend. And why is this good? Because in this way we can design our diodes having the exact geometry we want, depending on the output current we want them to have, depending how we want to use them. Then, as a next step, we did some material engineering. We doped our zinc oxide with aluminum, again using a solution-based technique. We have an aluminum pellet dipped in the zinc oxide solution for some time, and then we spin coat this solution on top of the pre-patterned electrodes. We see that the rectification is again quite high, and we don't see much change in the DC characteristics of the diodes. The important thing comes when we shift to the high frequency characteristics of these diodes. For this case, we use a different type of geometry, which resembles this one here. The reason for doing this is because of our RF setup, which has a specific separation between the source, the signal of the ground and the signal of the probes, and that's why we had to design a device that would be compliant with the configuration of our RF probes. Before getting to the results of the RF probes, let me show you some evidence we got to answer our own question initially, if the zinc oxide is actually getting into the gap or if it's just bridging the electrodes. And to prove that, we had again to go to high-resolution transmission electron microscopy, which we performed along with our collaborators in KAUST in Saudi Arabia. And we saw that both zinc oxide as well as the aluminum-doped zinc oxide fills the gap, and it's not only covering, let's say, the top of the electrode. So we were certain that the performance we could see, the electrical performance, was due to this material we fabricated. Capacitance, as I explained in the very beginning, is very important to radio frequency applications. And for this reason, to fully characterize our diodes, we performed capacitance studies to compare the zinc and the aluminum doped zinc oxide diodes. The doped diodes demonstrated a lower capacitance, although both types of devices gave capacitance below picofarad. And the fact that the aluminum doped devices had even lower capacitance gave us an indication that they would be beneficial for high frequency applications. The Mott-Schottky analysis on the capacitance voltance data revealed the presence of both deep and shallow trap states, as you can see here. However, from the analysis, we found out that the aluminum-doped zinc oxide film, the concentration of deep traps decreases and that of shallow trap increases. A mechanism we proposed for this is that the aluminum oxide anions that may be formed due to the presence of aluminum would fill some of the deep traps, while the aluminum cations may be substituting the zinc cations, providing extra electrons at shallow donor levels. And these attributes are expected to affect the high frequency operation of our diodes. Let's see if this is actually true. So here are results with the high frequency measurements derived from which we got by de-embedding the S11 single port measurements we obtained with a vector network analyzer. The intrinsic cutoff frequency in this case is defined by the intersect of the imaginary and real part of the impedance, and it signifies the highest frequency at which signals can propagate. Basically, it refers to the intrinsic speed of the diode as defined by the junction resistance, the junction capacitance, and the series resistance values. In this case, we neglect any transmission losses, any load resistance, and impedance matching losses, which are usually present in actual rectifier circuits. That's why this is, as I said before, the highest value we can actually get. However, it's still a significant figure of merit, which is used to assess the high frequency performance capability of our Schottky diodes. We see that both zinc oxide and aluminum doped zinc oxide diodes have very high cutoff frequencies at the 38 and 60 gigahertz, respectively. The aluminum doped zinc oxide performs better, quite as we expected from the previous analysis. And for this reason, we focus our study on these diodes from now on, and we see that if we apply the scaling also in the aluminum doped zinc oxide diodes in the high frequency measurements, we see that as we go from bigger diodes to smaller diodes, from 5 millimeter to 500 microns, the cutoff frequencies increases. And for the special case of the shortest diodes we measured and we fabricated and measured, the 500 micron diodes, the cutoff frequency exceeds the measurement limit of our instrument, which was 110 gigahertz. And by extrapolation, we can estimate that it goes around 330 gigahertz. To see now how our diodes would perform under AC field in a more, let's say, real life setup, we initially fabricated this rectifier circuit you can see here, where we have which comprises a resistor and a capacitor on the probe that was used to apply the voltage on our diodes. We saw that by applying an AC field of plus minus 3 volts at a frequency of 13.56 megahertz, a frequency which, as I explained initially, has a high commercial value. It's used in NFC tags and RFID tags in contactless cards and so on. We see that in that case, we got an output voltage of 1.1 volts for the zinc oxide and 1.5 volts in the aluminum doped zinc oxide diode. Now, to be able to see what happens if we move to higher frequency, higher than 13.56, we had to change a bit the setup and use this setup here. And this comprises a bias T, the diode under test, and the load resistor to measure the output voltage, a function generator that can go up to 20 gigahertz. And in that case, again, we see that the cutoff frequencies we get for, this is for the larger device, is above 3 gigahertz. The smallest device, as expected, shows an even higher performance, which goes up to 5.7 gigahertz. However, the output voltage decreases. So depending what's the application, if we focus more on the cutoff frequency or we care about the output voltage, we can switch to, we can select what the geometry of the diode will be. In the first case, we see that we get about 200 millivolts output voltage, while in the high frequency, in the smaller diode with a high cutoff frequency, we see that the output voltage is reduced to about 100 of millivolts.
Dimitra, 5 minutes more, please.
Thank you. To focus on the output voltage of these diodes at Wi-Fi frequencies, which is an important device characteristic, especially when we're talking about energy harvesting applications, we did expect that it would increase with the diode width. A 60 millivolt output voltage was obtained in the commercially relevant frequency of 2.4 gigahertz, which is relevant for, it's a Bluetooth frequency, actually. While we see that the 500 micrometers diode, the smaller ones, can still output above 40 millivolts up to 10 gigahertz. And again, a comparison of the aluminum doped with the undoped zinc shows that the aluminum doped is beneficial, as at 1 gigahertz, the output voltage is almost doubled in the aluminum doped zinc oxide. So to summarize my talk so far, I have demonstrated solution processed zinc oxide based diodes fabricated with coplanar nanogap electrodes. The undoped and aluminum doped zinc oxide showed high intrinsic above 100 gigahertz and extrinsic above 7 gigahertz cutoff frequencies with the A-lith fabricated coplanar electrodes. And we used inexpensive, easily processable materials, vacuum and solution processed organic materials. We used here only solution processed materials, and with this technology and the selection of this material, we see that we can outperform existing devices made with either organic materials that can be processed from solution or in vacuum, metal oxides, as well as devices based on silicon microparticles. Our devices compete directly with state-of-the-art radio frequency Schottky devices based on carbon nanotubes, on graphene oxide, on molybdenum disulfide, and tungsten diselenide. By using this low-cost, high-throughput, versatile technique and easily processable, abundant materials, we can approach the performance of CMOS integrated Schottky diodes based on silicon. So before I close my talk, I just would like to mention that apart from the RF diodes, we have in our group used these nanopatterned electrodes in many other applications, which have shown a very high performance, especially in terms of speed. In the response speed, for example, of photodetectors, we used perovskites as the active layer. We have demonstrated organic light emitting diodes where we deposited a light emitting polymer on top of those nanogaps to show fast switching LEDs. And this is something that I'm working with my current group here in Southampton. It's about memristors, either empty ones without using any material, or by using and selecting a specific material to give the memoristic characteristic. And with that, I would like to thank my collaborators from Imperial College who contributed substantially to this high frequency work. All of them have now moved to different posts, and my funders for providing the means to realize these devices and have these results. And finally, I would like to thank all of you for attending my talk today. I'm happy to take your questions. Thank you.
Thank you, Dimitra, for this pretty interesting presentation and subject. Now we begin with the question and answer session. There is a question, 2 questions from Aníbal Pacheco. Thank you for this excellent talk. Question number 1. There is a decade of difference between intrinsic and extrinsic cutoff frequencies. What is the most important extrinsic element hindering the practical response?
Yes, thank you. This is a very good question indeed. So it has to do with the material itself and the resistance, how to minimize the resistance in the actual device configuration. So as I said, the difference between intrinsic and extrinsic, it's not only the geometry of our devices and the material we use, it's also matching the circuitry and taking into account any other type of losses that happen when we use the circuitry I showed for the measurement of the extrinsic frequency. So we don't take these into account. We haven't optimized these parameters at all. We have only focused on the actual geometry of the device and improving the material. Then another thing I have not mentioned here is that the devices are some of them are encapsulated and some of them are operated in air. So until we find the proper way to encapsulate, of course, we will continue seeing this huge difference between the intrinsic and the extrinsic cutoff frequency in our devices. There are several things to consider here. For example, if we encapsulate, we add the capacitance on top of that. We have seen the effect of that also in intrinsic cutoff frequencies. But all these parasitic capacitances contribute hugely in the measurement of the extrinsic cutoff frequency.
Okay, thank you. Next question. Have you compared extrinsic cutoff frequency between doped and undoped diodes?
Yes, I showed you some results here, for example, which is a representative example at 1 gigahertz. This is extrinsic cutoff frequencies. And we see that as we expected, it's higher. It's higher also in the low frequency regime, in the 1356, so it's consistent. This improved performance at high frequencies of the doped diodes as compared to the undoped is consistent in both high frequency and ultra high frequency domains. And as I explained, the mechanism should have to do with the presence of shallow and deep traps in the doped devices.
Okay, thank you, Dimitra, for the answers. Now I have an extra question. Yes, Aníbal, thanks you for your answers. My question is, the cutoff frequency is affected by the resistance of the device, of the Schottky diode. However, which resistance? The resistance of the Schottky barrier or the ohmic contact, or both? That's my question.
Yes, both, basically.
Both. Okay. There is another question regarding for this technology of flexible Schottky diodes, which is the targeted operation frequency for developed your applications or different applications? Which operation frequency?
Yes, again, this will be defined by the particular application. So if it's something that doesn't necessarily need a long-range communication, for example, if you want to have a wearable device which you can read with your phone using NFC technologies, then 1356 should be fine. If you want a wearable device that can communicate in a longer range and use the Bluetooth or a Wi-Fi domain, then you should aim for higher frequencies. And having a look at the future, when the Wi-Fi frequencies used will be those of 6G in the gigahertz domain or hundreds of gigahertz domain, then we see the necessity of fabricating this kind of high frequency diodes to be able to communicate even directly with the cloud.
Okay. Okay, thank you, Dimitra. There is another question from Miguel Sanchez. First, congratulations for this brilliant presentation. Next, a study for Wi-Fi is presented, but at very high frequencies, around 100 gigahertz. Is a new version of Wi-Fi being planned beyond Wi-Fi 6?
I'm not the best person to reply that, I'm afraid. That's more a question for you, maybe.
Yes, of course. However, we thank Miguel Sanchez for this question.
Yes, I mean, we're not even in 6G yet, so this is already looking at the future, and we try to fabricate the devices that we will be comply with that. So what comes next, if there was a 7G or something, we'll see.
I think we can try to answer, but there is a question before the answer of this specific question. What do you think, which will be the best cutoff frequency with an optimized technology of flexible Schottky diodes, more or less?
The optimized frequency?
Yes, the maximum frequency this technology can reach.
Based on our results, we can target actually definitely 10 to 20 gigahertz as extrinsic cutoff frequencies. Okay. We can definitely go. I don't know if we will be able to reach the hundreds or go into the terahertz, but I'm very confident that by changing the material, we have also results recently. I didn't show them because they're unpublished yet, with IGZO, indium gallium zinc oxide, a different semiconductor, which is also processed from solution. And with that material, we have obtained even better performances.
Okay. Perhaps by changing the active material, we will reach better high frequency performances. That's another study. Okay, I think there's no more questions. Thank you again, Dimitra, for this excellent presentation. And I'll share my screen to read your diploma. One moment. Yes. The Instituto Politécnico Nacional, the Eugenio Méndez Docurro chair, presents this certificate of participation to Dimitra Georgiadou for her participation on the webinar, Terahertz applications based on emergent and high performance electronic devices, part 1, with the conference 100 gigahertz Schottky diodes for flexible large area electronics, given on the 16th of November 2021. Thank you so much, Dimitra.
Thank you very much.
And thank you.
It's my honor to be invited in your webinar.
Thank you so much. Just a last announcement. Tomorrow we will have 2 talks more. Please follow us in Twitter and the channel, the account Eugenio Méndez Docurro. We will begin at 16 hours Central Europe time. Thank you so much, everybody, and see you tomorrow.
Thank you. Bye.
Bye.
See you tomorrow. Bye.